Hello friends, now we will have some discussion on the design of limit gauges. We know that interchangeability is the ability to select components for assembly at random and fit them together within proper tolerances. Interchangeability is useful to attain close adherence to a specified size. It's not necessary that it should adhere to some exact basic size. The permissible variation in the size results into economical gain, but more system control and inspection are required. The inspection of the specific dimension of a component within the specified tolerance limit is carried out with the help of limit gauges. These limit gauges do not measure the exact size, but they only help to confirm whether the size under inspection is lying within some specified limit or not. There are different types of limit gauges. One of the primarily used limit gauge is a plug gauge. Plug gauge is used to check the internal diameter of a hole. Limit plug gauges have go gauge on one side and no go gauge on the other side. The go side should enter into the dimension and the no go side should not enter into the dimension. So go gauge is used to check the lower limit and no go gauge is used to check the upper limit. There are different types of plug gauges like pin gauge, taper gauge, thread gauge. From the figure on the left, it is interesting to note that the go side should definitely enter into the dimension and the no go side of the gauge should not enter into the dimension. When you try to understand the same using the figure on the right, the go dimension is adjusted with the lower limit of the tolerance zone. Similarly, the no-go dimension is adjusted with the upper limit of the tolerance zone. Now, what would happen if the go dimension does not enter the feature? In the figure, if you can try to visualize, if the go side does not enter, it means the dimension of the hole is smaller than the lower limit of the tolerance zone. So that is not acceptable. Similarly, what would happen if the no go side enters into the dimension? If the no go side enters into the dimension, then naturally the size of the hole would be larger than the upper limit of the tolerance zone. So again the dimension moves out of the tolerance zone, so that is also not acceptable. The second type of limit gauge is the snap gauge. Snap gauges are used to check some external dimension like the diameter of a shaft. Here also they have fixed go gauge and no go gauge on either side or on the same side. Similarly, there are adjustable snap gauges where the go and no go dimension can be adjusted as per the requirement. The outermost side is for the go gauge and the inner side is for the no go gauge. As in case of the previous gauge, here also the go gauge measures the lower limit and no go gauge checks the upper limit. Another type of limit gauge is a ring gauge, which is exclusively used to measure external cylindrical dimension only. So there are sets of go and no go rings which would be able to measure the external dimension. Ring gauges are also available for measuring the thread on a external feature. Now we come to the Taylor's principle of gauge design. This principle is stated by two statements, statement 1 and statement 2. Now, prior to coming to the statement 1, I would like to briefly discuss the figure in this slide. If you see the figure for the shaft, the upper limit is shown by the red circle and the lower limit is shown by the blue circle. There is another term which is known as maximum and minimum metal limit. Maximum metal limit denotes the condition where the part has maximum amount of metal, and minimum metal limit indicates that the part has minimum amount of metal in it. So for a shaft, the upper limit will suggest the maximum metal limit and the lower limit will suggest the minimum metal limit. As compared to shaft, when we observe the image of the hole, here also the red circle indicates maximum metal limit. In case of a hole, when the size of the hole is small, at that time the part will have maximum metal into it. So in case of a hole, the maximum metal limit is denoted by the lower limit and the minimum metal limit is denoted by the upper limit. Now, this Taylor's principle of gauge design discusses some aspects with respect to maximum and minimum metal limit. The statement 1 suggests the GO gauge should always be designed that it will cover the maximum metal condition, whereas a no-go gauge should be designed so as to cover the minimum metal condition of a feature. The feature can be external like a shaft or internal like a hole. Let us take an example with a hole. Suppose the dimension of a hole is 30 plus 0.7 plus 0.0. So here we understand that the upper limit is 30.7 and the lower limit is 30.0. Now GO gauge is meant to show the lower limit or the maximum metal limit in case of a hole. So the GO gauge should have the dimension of the lower limit of the hole. So GO gauge dimension is 30.00. So now if the GO gauge enters into this hole, then it is understood that the dimension is within the tolerance limit. Suppose if the GO gauge does not go into the hole, it means the dimension is even smaller than the lower limit. Suppose it is 29.9. So naturally this GO gauge will not go into it and hence it will not be within the tolerance limit and hence rejected. Take the case of no-go gauge. In this particular case, the no-go gauge should measure the upper limit of the hole, that is the minimum metal limit. So here the gauge dimension for the no-go gauge would be 30.7. If the no-go gauge does not enter into hole, it means that the dimension is within the tolerance limit. It can be 30, it can be 30.1, it can be up to 30.7. But if this no-go gauge enters into the feature, then it means the dimension is more than 30.7, that is outside the tolerance limit and hence rejected. So when you have a gauge, the GO gauge in this particular case will have a dimension of 30.00 and the no-go gauge will have the dimension of 30.7. Now let us try to understand the same principle of statement 1 with the help of an example of a shaft. Assume the dimension of a shaft is 30 plus 0.2 and minus 0.04. So the upper limit of the shaft is 30.2 and lower limit is 29.96. Now go gauge should be able to check the maximum metal limit. So in case of a shaft, the maximum metal limit is denoted by upper limit of the shaft. So the go gauge dimension would be the upper limit, that is 30.2. So as discussed earlier, if the shaft enters the go gauge, then the dimension is within the tolerance limit. Now let us understand no go gauge. No go gauge should identify the minimum metal limit. In present case, it is the lower limit of the shaft. So the no go gauge dimension has to be 29.96. If the shaft does not enter the no go gauge, then the dimension is within the tolerance limit. Now we will discuss the statement 2. Statement 2 says the go gauge should always be designed in a way that it will cover as many dimensions as possible in a single operation, whereas the no go gauge will cover only one dimension. For example, a go plug gauge, as shown in the figure, should have a full circular section and be of full length of the hole being checked. Now let us try to understand this statement 2 with the help of some examples. Let us consider the use of a go gauge for checking the dimension of a bush. If a short length of go plug gauge is used to check a curved bush, there are chances that it will pass through all the curves of the bent bush. So this will lead to wrong selection of the curved bush. Just imagine if the length of the go plug gauge shown in this image is doubled. Then a go plug gauge of a longer length would be available, which will not be able to pass through a bent or a curved bush. This will prevent the chances of wrong selection. So here it is not only possible to check the diameter of the hole in the bush, but it also helps us to check the straightness of the entire length of hole. Length of no-go plug gauge is generally kept quite smaller than the go gauge. Let us try to understand that with the help of an example of checking of dimension of a circular hole with the use of a no-go gauge. A pin gauge is used as a no-go gauge to check the upper limit of the hole, that is the minimum metal limit, across any diameter at any position along the length of the hole. Consider the case when the pin is kept horizontal. So here the no-go gauge does not enter the dimension, so naturally we are tempted to accept it. But when you turn this no-go pin gauge about the axis of the hole, then a defect of geometry appears. See the case when the pin is at the vertical position. At this position, the no-go pin gauge enters into the hole. It means that we will have to reject the feature. So here the no-go pin gauge is able to reject the non-circular hole because at one particular position the no-go gauge goes inside the feature. Similarly, take another example where we use a no-go gauge for measuring or checking the circular shaft. The no-go gauge would be in the form of a snap gauge. See the case where the snap gauge is dotted. This dotted snap gauge does not allow the shaft to enter into it. So the no-go gauge denotes that the shaft dimension is acceptable. But when this is rotated, the shaft is rotated, and the position shown by the full line of the gauge, then at that position the shaft enters into the no-go gauge. It means it goes into it, and hence the feature is smaller than the tolerance limit. So naturally it has to be rejected. Now there are certain guidelines for good gauge design. The form of go gauges should exactly coincide with the form of the mating part. Go gauges should enable simultaneous checking of several dimensions, and this dimension must always be put in maximum impassability. No-go gauges should enable checking of only one dimension at a time, and it must always be put in maximum passability. There are different materials which are used for making the gauges. As we know, the gauges are inspection tools that require very high degree of wear resistance and corrosion resistance. Further, it is required to ensure stability of their size and shape. Considering this, the limit gauges are generally made from special type of alloys by utilizing special processes. So different materials from which the gauges are made are ceramics, tungsten carbide, flame plated tungsten carbide, and certain alloys with chromium plating. Now we come to the discussion on gauge tolerance. For interchangeability, we know that it is not possible to produce something with the exact basic size, and hence a certain tolerance limit is permissible. Similarly, it is not possible to produce a go gauge or a no go gauge with the exact dimension fixed. So, gauge tolerance is provided on limit gauge to anticipate the imperfection in the workmanship of the gauge maker. Usually, limit gauges are made 10 times more accurate than the tolerance of the job. So, gauge tolerance is 10% of the work tolerance. Consider a shaft with dimension 30 plus zero point 0.1 and minus zero point 0.1, or a shaft with a dimension 30 plus zero point 0.2 plus zero point 0. So tolerance limit in either of these two cases is zero point 0.2 mm. So gauge tolerance, which is 10% of the work tolerance, is equal to 0.02 mm. Now, positioning of this gauge tolerance with respect to the working limits can be done by either bilateral tolerance system or unilateral tolerance system. But I would like to discuss that unilateral tolerance system is better suited for the gauge tolerance rather than a bilateral tolerance system. In bilateral system, as shown in this image, there is a possibility that some dimension may fall within the range of the gauge tolerance, but it may be outside the tolerance limit of the feature itself. Here the upper limit of the feature is 30.2 and lower limit is 30.0. So when you apply a gauge tolerance to the go gauge having dimension of 30.2, the upper limit of the go gauge comes out to be 30.22 and the lower limit is 30.18. Now this 30.22 may be acceptable for the gauge dimension, but it falls outside the overall limit of the tolerance and hence it would be rejected. Similarly would be the case when you consider the dimension of 29.98 at the lower limit. This dimension will also be rejected. Compared to this, in unilateral system, the gauge tolerance is included in the work tolerance. So the entire range of the gauge tolerance will merge with the work tolerance. So only components which are within the limit are acceptable when a unilateral system of gauge tolerance application is utilized. Now some discussion on wear allowance. We know that the measuring surface of limit gauge would constantly rub against the workpiece surface, which would result into wearing of this gauge surface. So there are chances that the size of a go plug gauge is reduced and the size of a snap or ring gauge is increased due to such wear. Wear allowance is provided to compensate the wearing of the limit gauge surface. Usually, the wear allowance is provided as 1% of the work tolerance, that is 10% of the gauge tolerance. So, wear allowance is applied generally to a go gauge and it is not required for no go gauge, as wear would develop on a no-go gauge in the direction of safety. So that would in a way help. This wear allowance should always be added to the dimension in case of a plug gauge and should be subtracted in case of a ring or snap gauge. With this understanding of the Taylor's principle, few illustrations, and the requirement of gauge tolerance and wear allowance, I am very much sure that it is possible to solve various problems given on this topic in the textbooks. For further understanding and solving different numericals, two specific lectures in the NPTEL course are also praiseworthy. Thank you very much.